Okay, so we're going to talk about the equilibrium constants that we just learned and the consequences of these equilibrium constants when it comes to reactions, especially with respect to the magnitude. How can we interpret what the magnitude of these values say about a reaction? So, first point I'm going to make here is that if Kc or Kp or any other Ks that we're going to learn about later on, if those values are large, that means that the reaction essentially goes to completion. All right. So basically, what that means is that all the reactants are used up if Kc and Kp are huge, right? On the other hand, if Kc or Kp is small, then the reaction is only moving forward to a slight extent, which basically means that you have a lot more reactants and products involved in the system at equilibrium. All right. Another thing, very important point to be made here is that the equilibrium constant only applies to the system at equilibrium. So what that means basically is if the concentrations are at equilibrium concentrations, then when you plug those values into the Kc or Kp expression, then you're going to end up with a constant. If those values are not equilibrium values, then the resulting Kc or Kp calculated would not be correct, all right? In fact, it would be a different term. It would be called Qp or Qc, which we're going to learn about later on, all right? Now, another thing I want to mention is that even though you might have a reaction that has a large Kc value, it does not mean that the reaction will go at a fast rate. So therefore, there's a difference between what we say with respect to reaction, that it is thermodynamically favored compared to kinetically favored, right? So in the case of a thermodynamically favored reaction, which involves a large Kc or Kp value, it tells you basically the probability of the reaction taking place, but it doesn't say anything about the speed of the reaction. So the fact that a reaction has a large Kc or Kp value does not mean that the reaction is undergoing a change at a very fast rate, all right? It just basically means that the tendency of the reaction to form products would be very high, all right? And that is basically what we call a thermodynamically controlled reaction, where the amount of product is based on the large Kc or Kp value. On the other hand, if the reaction is kinetically controlled, basically what that means is that the reaction proceeds at a fast rate. Does not necessarily mean, however, that you're going to get a large amount of product, because, of course, it's possible that the Kc or Kp value would be small. So we have these two factors to contend with when it comes to product formation. And for those of you who plan to do organic chemistry, you're going to see this at work in a lot of different situations where under certain circumstances, the reaction would be thermodynamically controlled, and then under other conditions, the reactions would be kinetically controlled. Okay, so let's look at this example. It says, is the reaction, and it gives the equation, likely to occur to any appreciable extent at 298 Kelvin? And it gives you the Kp value as being equal to 5.3 times 10 to the 22. Well, just by looking at this, the answer would be yes, simply because the Kp value is a large value. 5.3 times 10 to the 22 is a very large number. So therefore, what that tells us is that the reaction will take place favoring the products as opposed to the reaction, or as opposed to the reactants, all right? And that's basically all you can say about this. Okay, so let's move on now to the discussion of something I briefly alluded to earlier, the reaction quotient, Q. Now, remember we talked about Kc, right? Kc is equal to basically the concentration of products over reactants, but remember, in that expression, those concentrations must be equilibrium concentrations. Well, Qc or Qp, depending on whether or not you're dealing with concentrations or gases, whether or not you're dealing with concentration or pressure terms, is basically the same expression as Kc or Kp, excepting that the concentrations or the pressures of the gases are not at equilibrium. So basically, Qc or Kp is the ratio of products over reactants at any time, all right, including equilibrium, All right, so that's what QC or KP is. And it's useful because we can use it to predict the direction in which a net change will occur in order for equilibrium to be established, right? All we have to do is make sure that we compare, for example, the QC value to that of KP, or the QC value to that of KC, or the QP value to that of KP. All right, so let's look at this slide here, which illustrates what would happen in order for a system to achieve equilibrium depending on the reaction quotient and its relationship to the Kc or Kp value. So at one extreme, we have Q being equal to the concentration of the products divided by the concentration of reactants. And you see that there are no products here, right? Which basically means that there's only reactants present, and therefore the reactants will react to form products. So therefore the net change would be from left to right, because remember, traditionally speaking, the reactants would be on the left side of the equation, the products would be on the right side of the equation. So therefore, in this particular instance, in order for equilibrium to be established, the reactants will react to form products, and therefore eventually the system will achieve equilibrium. So therefore there will be a general shift from left to right. The same is true if in this situation where you have the amount of products being so small such that the Q value is less than K, right? Now, in order for the system to achieve equilibrium, the value of Q must increase, which means that the amount of products must increase and the amount of reactants must decrease. And that change will occur until you end up with your products. In other words, the reaction, generally speaking, will be shifting to the right, and you end up with the equilibrium being established. So if Q is less than K, then the reaction will shift to the right, favoring more products, decreasing the concentration of the reactants until Q becomes equal to K, and therefore the system will achieve equilibrium. And then we get to the equilibrium situation where the Q is such that the concentration of products divided by the concentration of reactants is equal to K. So therefore, at that point, the system is at equilibrium, and therefore, there's no net change in terms of which direction the reaction will shift. Now, on the other hand, if you have a situation where Q is greater than K, that means that the amount of products is too large, and therefore, the reaction will shift in the reverse direction. In other words, from right to left, to form more reactants and decrease the amount of products until Q is equal to K. And then at the other extreme, where you have no reactants and only products, what that means basically is that the products will themselves react to form more reactants, and therefore the reaction will shift from, again, right to left, and therefore that will continue until the Q value decreases to become equal to K. All right, so those are the possibilities, and therefore you can make certain predictions if you have a system where you have a certain amount of reactants, certain amount of products. Using this guideline, you can predict whether or not the reaction will shift to the left or to the right in order to reestablish equilibrium. All right, so that's basically what this is all about here. Now, this brings us to a very important principle known as LeChatelier's principle. And let me just say that I know I'm mispronouncing Mr. LeChatelier's name because he's French. There's a French pronunciation which I think is LeChatelier or something like that. But I'm so used to pronouncing his name as LeChatelier, so please forgive me for doing so for the rest of this topic. So, what does LeChatelier's principle says? Well, basically what LeChatelier's principle says is that whenever you have a system in a state of dynamic equilibrium and you make a sudden change to either the pressure, the temperature, the concentration, or the volume, then the system will respond so as to counteract those changes in order to reestablish equilibrium. Because the thing you have to remember is that whenever you make any one of these changes to the system, you're disturbing the equilibrium. You're adding a stress to the system. According to LeChatelier's principle, the system will try to relieve that stress by counteracting the change you're imposing, right? So let's say, for example, the system is at equilibrium and you change the concentration of one component in the system. Well, according to this principle, the system will try to decrease the concentration so as to reestablish the equilibrium that you have disturbed as a result of increasing the concentration of that component. And the same is true, or I should say the converse is true, if you try to decrease the concentration of a substance involved. the system will respond by trying to increase the concentration so as to reestablish equilibrium. And the same argument can be applied to change in temperature, change in pressure, and change in volume with respect to gaseous systems, all right? So that's basically what LeChatelier's principle is all about. So for example, let's look at concentration changes. Now, at equilibrium, we know that Q is equal to Kc. If the concentration of one of the reactants decreases, then the denominator of the reaction quotient will increase in response, all right? So therefore, Q is now less than Kc, all right? So the system will no longer be at equilibrium, right? Because Q is now less than Kc, not equal to Kc. The system is basically not at equilibrium. But as stated here, the concentrations of all the species must change in such a way so as to make sure that Q is increased so that it's equal to Kc, right? And in order for this to happen, the concentration of the products would have to increase. In other words, there will be an equilibrium shift to the right from the reactants to the products, all right? So basically, let me just, try to explain it further by squeezing something down here below. So if you have reactants going to products, right? And all of a sudden, you increase the concentration of the reactant, all right? That means the system is not at equilibrium anymore, right? So this is the reversible reaction, right? So the system is not at equilibrium anymore. So the system will try to decrease the concentration of the reactants. And the way the system does that is that some of the reactants will react and shift the equilibrium position towards the product side, right? So therefore, at the new equilibrium position, the concentration of the reactants will decrease while the concentration of the products will increase, all right? So you're going to end up with some different concentrations, but the equilibrium will be restored. Okay, so that's a hypothetical example, a real example. Now, this example is a reaction between acetic acid and 1-octanol. Now, I won't write down the formulas for all of them. It's going to take too much time. You can look them up on your own. I'm just going to kind of abbreviate things a bit. So HA would be your acetic acid. And 1-octanol, I'm going to use OC to represent 1-octanol, right? And that will give you OCA plus, let me put OH here because octanol has an OH here. That's very important to form OCA and H2O, right? So OCA would be octyl acetate, right? So I'm just using these abbreviations because the formulas for these compounds are rather long. It will take too much time to write them down. In any case, basically this is what happens. You're starting from 0. This is time 0. And the only two substances present at time 0 would be acetic acid and 1-octanol, right? And then the reaction takes place. So as the reaction takes place, the concentration of the products of the reactants decreases, and the concentration, let me go back to my pointer function here. Okay, whoops. Let me do this. Okay, so as I was saying, the concentrations of the reactants decreases, going down here, while the concentration of the products increases going up here, right? And then you get to an equilibrium state where the concentrations are constant, right? So at equilibrium, all of a sudden, you add acetic acid present, right? So when you add acetic acid present, what happens? Well, as we said before, the system is no longer at equilibrium. So therefore, what will happen is that the concentrations of both reactants from that point on will start decreasing, right? So the concentration of acetic acid is increasing from here to here at equilibrium when you add the acetic acid, and then the system tries to achieve equilibrium by reducing the concentration of the acetic acid. There'll be a corresponding reduction in the concentration of 1-octanol. At the same time, you'll have an increase in the concentration of water and octyl acetate, right? So you end up with a new equilibrium position here. And that's basically what happens when you all of a sudden add a reactant to the equilibrium mixture. You have basically a shift so as to reduce the concentration of the added component so as to restore equilibrium. All right, so that's what happens in this case. And we can also have, based on this idea, an explanation for what happens if you decrease the concentration of something, and you can argue your way into what will actually happen. All right. Okay, so let's look at this example, which is actually based on the same reaction. And in fact, this is the equation that I did not write on the previous slide. So this is your 1-octanol, this is your acetic acid, this is your octyl acetate, and this is your water. And the question says here that water can be removed from the equilibrium mixture in this reaction by using a drying agent that is insoluble in the reaction mixture. Describe how the removal of a small quantity of water affects the equilibrium. Well, it's based on LeChatelier's principle. Basically, when you remove water, you're reducing the concentration of water here, right? Which means that the system will try to restore the water that is removed, and therefore the equilibrium will shift from left to right. So therefore, the system will try to replace the water that is removed. In so doing, the system will also increase the amount of product, right? So therefore, the concentration of the product will increase, and also the concentration of 1-octanol and acetic acid will decrease, all right? So that's basically the explanation to describe the effects of removing water from the system, how it will affect the other components in the system based on LeChatelier's principle. Okay, I'm going to stop here, and the next topic will be discussing heterogeneous equilibria and how it relates to LeChatelier's principle. All right, until next time.